Okay, so at the end of the last video, after the end of the last video, I actually went and finished the entire project, or at least finished it up to a working point. There's a lot of improvements I want to make, but we'll get to them later. So this video is basically just going to be a recap. It's going to probably be very long, but if you're interested in learning what I did and why I did it, this is definitely a video you should be watching. So at the end of the last video, I'm pretty sure I forgot to put in unsolved board equals here. If that's the case, make sure you're aware of why this should be here, and yeah, make sure it's in your code if you're trying something similar to this. So that's all for this bit. Now, solved board returns an unsolved board, and so up here in main, we return a solved board. It returns a solved board. It's called unsolved board in the function. So we take the solved board, then what we want to do next with it, this is all new stuff, so we want to find the list of moves. So we can't just take a solved board and then draw from that. What we need to do is we need to find some way of saying, right, we're going to start with red, and now red has to go down, and then it has to go down again, and then down again, and then down again, and then it has to go right, and we have to find some way of making the mouse do these movements. So to do this, what I figured was I would create a list that would contain an array of all the different colours, like what their respective moves are, so we could just then loop through that list to find what the moves for each colour were, and then loop through each array to find what exact move should happen when. So what we would have to do is have this function output arrays that would be numbered moves. So you'll see how I did that in this function down here, so move finder. So what we're going to do to start with is we're going to create another board with X, similar to how we did in the solved board function. So we create a board with a border of X's that's 2 bigger than the board we're using. Then we populate the whole thing with X's. Then we populate it with the board that we, like the ends of the board, sorry, like this is the unsolved board we're populating it with. So it's basically going to be all X's except for the ends of the board. Now this is the unsolved board with X, as you can see here. We also want a solved board with X, so it's going to be the exact same thing, but instead of populating it from the unsolved board, we're going to populate it from the solved board. So if I actually comment all this out, we might be able to see that. Okay, so you can see there, maybe if I put these on separate print functions with a blank space between them, it would be clearer. Okay, so you can see what we've done here. We've got this is the unsolved board with X right here. So you can see we've got a border of X's, we've got empty spaces, and then we've got the ends in lowercase. So the other one we have the solved board in here, surrounded by X's. So that's what the solved board with X and unsolved board with X are. Hopefully that makes sense now. So next step, we had to remove the zeros out of, oh no, sorry, just before this, we colours in board, so we want a list that's going to tell us what colours we're working with, because obviously the list of colours I have, if we can find that somewhere, so the list of colours are basically all these here. We have a lot, and we're not always going to need them, so I figured rather than looping through them all, we may as well just find the ones that we need. So colours in board list, that's going to be empty, we don't know what colours are in the board yet. List of array of moves, this is going to be what we return at the end. This is going to be the thing I talked about earlier. It's going to be a list of array of moves we need to take. So that's also going to be empty, we don't know what these are yet. Now for I in the inner of the board, so this is going to be the important bit, the bit without the X's. If the unsolved board, so we're going to loop through the unsolved board, every position in it, the one with X, but we're only going to loop through the inside, so we're going to loop from this R here to this 0, like this rectangle here. We're going to loop through all these inner values, and we're going to say if the letter that we've got there is not in the current colours with board. So the first one we loop through is going to be R. Now R is not in colours in board because it's empty. So because it's not in, we're going to add R to this colours in board. So now this will contain R. And then we're going to say, right, move on to the next one. So basically what it's going to do, it's going to loop through every single square, and it's going to say, if you're not already in colours in the board, you are now. So this is basically just going to find out what colours we're working with. Then it's also going to take zeros because we've got a lot of zeros on the board. It's going to find one of them at some point. So at the end we're just going to remove that because that's obviously not a colour we're working with. So we could return colours in board at this point, but hopefully you get the point. It's just going to return an array of all the letters we're working with. So lowercase r, lowercase g, lowercase b, lowercase y, and lowercase o. That's all it would return for this board, these 5. It doesn't return doubles because, well, hopefully you see why not, because of this bit right here. So next up, this is the main bulk of this function. So this might not make a lot of sense, but we'll run at the end and hopefully you see. So we're going to loop through all of the colours in the colours in board. So that's going to be those 5 letters I just talked about. Now we're going to transform the colour to an uppercase. This is just so that it matches this casing right here. So this will work better. You'll see soon why. Then we're going to count the number of that colour that we found. So for example, if the colour we're working with is red, then we're going to find 1, 2, 3, 4, 5, 6 reds, and then that's going to, whoops, and then that's going to be the returned number of colour from like this little function here. So loop through the board, that's what this bit does. If solved board with X is equal to colour, number of colour plus equals 1. So you can see, because we're starting on 1, this is actually going to find 1 extra, but the reason I've done this is because the way Python does the range function here, it'll do the range from 1 to number of colour, not including number of colour, but including 1. So basically I didn't want it, because it just started 0 indexing basically, I didn't want the 0 in, I wanted it to just be move 1, move 2, move 3, rather than move 1 is equal to the 0th index. I just basically want to shift it all along. Hopefully this makes sense in a bit. So what we do once we return this number of colour is I create a list that is a list of it's a list of indexes. So it's a list of the numbers in this range. So this generator is going to produce all the numbers from 1 up to number of colour. So like I said for red, there's 1, 2, 3, 4, 5, 6 here. It's actually going to return number of colour equal to 7 because of what I just talked about. So when we range from 1 to 7, we're going to get the numbers 1, 2, 3, 4, 5, and then 6, not including 7. So there's going to be 6 numbers in this list. And then that's going to be the list we can take our moves from. So the reason I did this was because if you look at orange here, sorry, we'll look at red again, we've been working with red. So if red moves down here, and then it finds that this red can move up here, you can see this end stops and can't be drawn from anymore. So we can't have the draw function, draw like this half and then have them meet in the middle. It has to draw continuously from one half. So what I wanted to do was allow it to solve the board from both sides, but when it actually came to draw time, it would realise, right, I've got to start at this end and then just follow the solution all the way. So what this is going to do is it's going to give it a list of available numbers, and we're going to always, when we go through our moves, start at number 1, put the mouse there, and then draw from 1 to 2, 2 to 3, and so on until all the numbers are gone. So hopefully this makes more sense in a bit once we start printing stuff out. You'll see. So we've got array of moves. This is going to be the thing that gets put into our list that we return right here. So this is going to be a list of array of moves. This is just going to be one array of moves. So the array of moves that's specific to this colour. So this is going to be an empty matrix here. This is when we initialize the matrix. Then we're going to loop through the board, and we're going to say loop through the entire board this time. So this is going to be sorry, no. So what I did here, you'll see now a lot of indexing will not make sense here because I did this a different way initially, and then basically went back through and I was quite lazy and just edited these indexes rather than changing the entire board and entire code again. So this is actually going to loop through the same thing as what's looped through here. So like it's going to loop through from 1 to size of board plus 1. Basically it's going to loop through the inner of the board. Now the reason it doesn't look like it here is because of these indexes. So the indexes are like I plus 1 and j plus 1, so it's obviously adding 1 to these as this range does here. So basically instead of having the range add the 1 on, I've now got it in the index instead. So basically just think of it, it's the same thing, it's just going to loop through every available square. So hopefully that doesn't throw you off too much. So we're going to loop through every available square, and we're going to say, is that square equal to color.lower? So up here we changed it to color.upper, but for this specific case we actually need the lower. So what we're going to need here, this is looking for the ends. So you can see we're looking through unsolved board here, so we're looping through this one right here. So we're looking for these end values, and we're going to say wherever these are, we want to take, if the list of index 0 is 1, so if we've still got that first element in this list, then we want to set the array of moves ij equal to list of index dot pop 0. So what this is going to do, it's going to take the first element of list of index, it's going to delete it from that list, and it's going to instead put it in the array of moves ij position, which is where it's just found the lowercase color. If the index 0 is not equal to 1, so we've already took the 1 out somehow, which would be only by finding the other end, then we're going to take the last element instead. So what this bit does here, this loop, it's going to loop through this function, and it's going to say, right, we need to find both ends of R, and what I want to do is I want to label one of them 1, and then I want to label the other one the last number, which in this case would be 6. So I have 1 here, 2, 3, 4, 5 and 6. So it's going to find the first one, label it 1. It's going to find the last one and label it 6, because it knows that the last one's going to be the last move and the first one's going to be the first move. So that's how we're going to get our first 2 moves. Now if I print array of moves right here, you should be able to see, hopefully this works, you should be able to see what I've just mentioned. Yeah, so we see here for each color we find the first move, so this is for red right here, so we find the first move and we find the last move and we number them. Then we do green, so we find the first move and the last move and we number them. So you can see it's finding the first and last exactly as we expected. Now I could print the list of index and stuff, but I'm pretty sure you'll understand that. It's basically just a list of the available moves. So if it's 6 long, if the list is going to be 6 long in our grid, we know the available moves is going to be 6 moves, so there's going to be 6 numbers to choose from. So after we've got the ends, this is now where we loop over the basically while there's still a move in this list of moves, while that's greater than 0, we're going to loop over the board repeatedly and find out what our next move should be. So this logic here is all the way down, actually. I think it's all the way up to here. This logic is very, very similar to the forced move check logic right here. So it's very, very similar to this logic. It's just got a little bit extra in. So I basically copied it over and just changed the indexes around and stuff. So if you understood that, you'll be able to follow along with this, hopefully. So right here, this part here checks the current square, and it says if it's equal to list of index 0 minus 1. So what this will be is it'll be This will be the current lowest number in the index, in the list, sorry. And then we're going to take 1 from it to find the number that was just put in the grid. So when we've got these grids over here, we've got a 1. Now a 1 is not in the list anymore, the lowest number now in the list. Well, the list is going to contain, for this case down here, actually no, let's stick to red, okay? I'm going to stick to red the whole time. So it's put 1 in, it's put 6 in, it's now got 2, 3, 4 and 5 remaining in the list. So what we're going to do is we're going to say, take the 0th element, which in our case is 2, and now we want to look for, not 2, we want to take -1 off it, so we're going to find 1. We're going to look for the position of the 1, and we're going to say, for that 1, we now know our next move is somewhere adjacent to it, so we know it's here or here. Basically, this takes the last move and it checks the adjacent square to check. This is going to be our next move. Now, it's going to be one of them, so this is basically checking which one it is. It does this for the low numbers, and then it does it for the high numbers as well, because sometimes, obviously, it's probably not going to happen in these simple boards, but you can imagine, hopefully, if you had something like this, whoops, if you had something like this, this is forced in here, and then this isn't forced anywhere because it's got reds either side of it, so you'd have to have like the red come back up. So say this red went through this blue and then up, like you'd then have it forced in from the other side, and then you could solve it from the other side rather than having to just follow one chain all the way. It's not too clear yet, but basically this is hoping to fix problems later on and fix potential issues that might come up. Obviously for this one we could have just said find the lowest number, check the adjacent squares, find which one is the next number, fill it in, then go to the next one, then the next one, and so on, and just continue until the list of moves done. So hopefully this line makes sense to you. If not, let me know. I'll try and explain it a little bit better. Now, this bit, like I just said, is all logic from the force move part of the solution. So what it does is it checks the squares. Basically, you can have a read through this yourself. Hopefully it makes sense. It's basically just going to check the square and say, is it forced to go right? Is it forced to go left? Is it forced to go up? And what it's going to do is, if it is, it's going to replace the solved board. Okay, so it does a couple of things right here. So if it's working with the low number, so say it's found like where the next move should be a low number, this is checking that, and it's going to fill that in with the first index of the list of indexes. Then it's going to replace solved board with X with a 0 to let us know that we've now finished that square. Else we know we're working with the high numbers, so we're working with like, so this would be the low number side, this would be the high number side. We need to know which side we're working with so we know which end of the list to pull from to draw a solution. So this is what this does. It takes either the low number or the high number and then fills it in. Now, it does that for right, it does it for left, it does it for up, and it does it for down. And then what it's going to do once it's done these is, if the length of the index, like if the length of the list is equal to 0, it's going to break. It's also going to do that again, it's going to break out of here. So it's got this for loop to break out of, it's got this for loop to break out of, and then finally it can break out the while loop. I had a lot of issues, it took me quite a long time to figure out why it wasn't breaking out when this while loop was satisfied, but for some reason it insists that the for loop has to be finished. So you need that in. So what I'll do now is, and then once it breaks out of these, it's going to know that it's found because the list of indexes, it's now got 0 in there, there's no element in there. We now know we've completed the array of moves. So what we're going to do with the array of moves is append it to the list of array of moves. So hopefully when I print list of array of moves here, you'll see. And what I'll do as well is I will print, right before this, I will print array of moves. and I'll just put a line in here. So what you see here, so we found our solution board. This is our solution board printed out. Then we found our red moves right here. This is the array of moves. So this is, sorry about that, hold on. That feeling when people just won't stop chatting, man. Okay, so this array of moves right here, sorry about that. That array of moves is printed right here. Then we print a line, so you can see the empty line printed up here. Now it's going to print the list of the array of moves, so you can see it tells you the first element is an array, and this is that array. So this is exactly what we've got here, just a little bit easier to read up here. So that's the reds done. Now it does it again, it finds the greens, so you can see it's filling it in with numbers. So it's going to say this is the first move, second move, third move, fourth move, fifth move. So if we draw this out, first move, second move, third move, fourth move, and fifth move, we know we've just solved the green. So this is working. Now it appends that to the list, and you can see now in the list we've got the red moves, and then we've got another array, and that's the green moves. Obviously it's slightly off axes, just because, yeah, hopefully you understand that like this is actually right, it's not randomly over here. And yeah, it's just going to loop through, find all the different moves and append them to this list. So you can see at the end we've got the red moves here, we've got the green moves, then we've got probably the yellow moves, I think this is, and then we've got the blue moves, and then finally we should have the orange moves, which we do. So we've got every colour, all the moves it should have, all in this one list. So if I delete all this print functionality now, because we don't need this anymore, we return the list of moves, and now we need to draw from it. So I could leave this print in here, this might make sense, then you'll just see the list of moves printed out beforehand. So next function we have to put in is a draw solution function. So this is going to take the list of moves we just output, and it's going to draw it. So it's going to take in the list of array of moves. It's also going to take in the board of pixels. You might remember this from probably episode 3 or something, where we returned it here and then we never used it again. So this is going to be all the pixel values we need of all the squares. So if I comment this out and just print out the board of pixels, so you can see we've got our our list of array of moves up here, and now our board of pixels. So you can see 74 long is where this entire column is, and then it gives you all the y coordinates of this column. So you can see we've definitely got all the coordinates of all the squares. This can be really useful. It makes our next function quite nice, quite small. So we delete these print functions, we don't need these anymore. Now we're going to take in board of pixels, we're going to take in a list of array of moves. So draw solution right here, you can see it's not too long a function. So for I in range length of list of array of moves, so what we're going to do is we're going to basically loop through all the different arrays in this list. The current move to do is, current moves to do is the first array. So we're going to take out the first array and put it here. So you can see here, if I print current moves to do and then just comment that, so you can see for each of these eyes that it's going to loop through, it's going to print out the array. So it's basically doing the reverse of what we did down here. rather than appending to it, it's just going to pull one from it. It doesn't actually delete it from the array, but it's just going to pull one from it. So we're going to get back the original array of moves. This is basically just so that this can return a list that's like n elements long, and then I can pull them all out here, all n elements as individual elements. So delete this now. So we've got the array. Now the first move we're going to make is obviously move number 1. So we set move number equal to 1. Now while true, so it's just going to loop until we break. We're going to say location underscore data. So this is going to be the pixel value of something. So you'll see here. Sorry, it's not the pixel value. It's the row and the column value. I'll print this out actually, because this function is one that I hadn't seen before until I looked it up for this project. So you can see here all the different things it's printing. Whoops. Oh, I'm stuck in an infinite loop here. Whoops. So if I, instead of this while true, if I just copy this, put it up here for now. This might work. Okay, so this is just going to do for like the first move of each array, because obviously I've just pulled it out, but I just want you to see what this this numpy.where function returns. So you can see it returns for move number 1 of the reds. So this is going to be the first line. This is what this is doing. We're just going to focus on this line. So for move number 1 in the reds, we know that is the very first element, because the reds appear. So it's 0 0. So it's going to return the row and the column like position, and it's going to say what data type they are. So d type equals int 64. So it's a 64-bit int. I think that's right. So I can delete this now, because obviously this is definitely in the wrong place. We want this originally where it was. Actually, whoops, we don't want this. No, stop. Okay, so we see what this returns. It returns the tuple, this tuple right here. Now we're gonna say, once I've got rid of this print that we don't need anymore, if the length of location data is 0, so if the length of this this tuple right here, I think, yeah, so this is, it returns an array, sorry, it returns two arrays in a tuple. So the first array is the position and the data type, second array is the position and the data type. So we're going to check this first tuple, is it equal to 0? If so, break, because what I realised was if we do numpy.where on a current moves to do that is not in, on the move number and the current moves to do. So basically what we're saying is in numpy.where, sorry I forgot to mention this, the arguments you pass is you pass where are you looking and what you're looking for. So we're looking in current moves to do, we're looking in this array, and we're going to say where is the current move number. So move number is 1, where is 1 in the current moves to do, and obviously it returns 0 0. So I realised what it returns if it doesn't find 1 is empty. So basically this thing here checks if there isn't 1, then we're going to break, because we know we've finished all the moves. This is basically our break condition. This, you'll see, this is the only place we break in this whole thing. So next to do, we've got row index. This is location data 0 0. So this can be from the reds, it'll be 0. Column index is location data 1 0. So again, this can be 0 for the red one. Now x coord and y coord is board of pixels, row index, column index. So this is going to take the 2 coordinates here, and it's going to go to them positions in the board of pixels array. and now return those as X and Y coord. This gives them as actual screen pixel values, so we can work with moving the mouse to them. Now, if move number equals 1, why are we passing here? Pretty sure these passes are only in to not quite sure why those passes were in and then why it was still drawn earlier, but we'll see if this works, okay, when I've deleted them. So if the move number is equal to 1, we only want to move to that position, so move to, because we're not clicking anything, dragging anything, we're just literally going to move to it, so we're going to move to this position right here if it's 1. Now else, we're going to drag to it from where we are. So for move number 1, okay, say the mouse is right here, for move number 1 we move to here. Now for move number 2, it's going to go to the else, it's going to hit that, so it's going to drag to the next position, so it's going to drag down here, so you can see it's going to do this. Then it's going to drag to the next one, drag to the next one, and you can see after each move we iterate through this move number thing. So this is going to now look for the next number rather than looking for the same number again. Now, obviously, each time it does that, it's going to be really fast. So I put this time.sleep little bit in here so we can actually see it all drawn out. What I will do as well is add a duration into here, so you can actually add durations in by AutoGUI. So you'll be able to see everything going on, hopefully, at a nice speed. So let's run this and hope for the best. Okay, so you see it's moved to the red. Let's drag down. To drag down again. Let's drag down again. And again. And now hopefully drags right. There we go. So now it's gonna again find a 1, so you see it moves to, it doesn't drag to, and then it drags again. So it's really important that we move to the next one and not drag to the next one, because if we drag it could mess up the board depending on like positions. So yeah, it's finally working, it's finally doing stuff that's useful. So hopefully it makes a lot of sense to you now why we were doing things the way we were. So yeah, I'm just going to break out of this now. This is pretty slow with all the durations and stuff in. I'm going to have a little bit of fun with it at the end before I finish off this video. So if we remove these durations and then reset the board, we can see straight away huge like speed improvement. You'll see there's just like a 1 second sleep between each one, so you see the mouse moves instantly now, or near enough instantly. So if I break out of this, and now what we're going to do is I'm going to remove the sleep function. So we're going to see how fast this one goes. And now you'll see it's still jumping about. There's a slight delay. So one thing I looked up is I looked up how to remove that failsafe, because it's a failsafe so that the PyAutoGUI isn't just constantly taking over your mouse. But since I'm pretty confident it's working, I figured let's remove the failsafe. Would not recommend doing this if you don't actually know your code's going to work properly. You might lose control of your mouse. So what you do is you set this PyAutoGUI.pause parameter here. You set this equal to 0. So by default I think it's 0.1. So I'm changing it to 0. So the idea is it's going to be instant. So if we do that and run, you'll see instantly solved. So now I thought, right, so it could solve this board, and also just to show you it can do bigger boards, here's a 7x7 that it can't solve. Brilliant, good example. Can it solve this one? Ooh. What boards can it solve? Interesting. Okay, there we go. So it can do 6x6s. Now the reason it's not doing the 7x7s is because apparently they're not all forced moves. Let me check that, because I don't believe it. definitely looking like it's a forced move. Although maybe it's not. Yeah, it is. It's definitely forcible. Yeah, let's have another look. Okay, I might have a look at that after this video. I don't want to make this any longer than it already is. It's probably going to be about a 45-minute video as is. So, what I did next, after realising it could do these boards quite easily, is I went to the time trial, and now you'll see I've got 10 solved. Definitely did these by hand, I'm definitely that good. So, all I did was, I created this loop, so I just loop back to main after each time we solve a board. I also added a sleep because you'll see when the boards change, they're not instant. My program's actually faster than it can change boards. So, yeah. So we've got this times.sleep, we've got the call of main again. Now I'm going to save this. I'm going to get ready to hit that and go. So we'll see how many it can do. Now you'll see some of these boards can't actually be solved by it, and I'm going to get to this in a minute, but you'll see it flies through them. And yeah, we'll see how many it can do in 30 seconds. Might actually be 10 here if it gets all boards it can solve. Okay, so there we go. We found a board here that it can't actually solve. Not too sure why, but because there's no initial move, so you'll see none of there's no actual colours here in these four, by the way. Hopefully you can tell through this thing, because as soon as I click play again, this board's going to disappear, but you can see there's no actual move initially that it thinks is forced. And now I can see something straight away in this board that I personally would do because I know it is forced, but it's just not coded in this. So you can see we've got a green here, we've got a red here, and we've got a red here. Now the only way to occupy these two squares here is to have them go red. So we'd go through here and connect these reds. But the game doesn't know that because it sees the red and it goes, right, well this red can go here or here, and now this red can go here or here. So it doesn't know that they have to go up. So I'm not sure how I'd code this in, but it's definitely something that can be done. So I might look at this. Obviously this code over here is really modular now. It can be improved quite easily. I just add these back in. And I also get rid of this. So it can be improved quite easily because of the solve board function over here. I just need to, here where I've got run next function, I just need to literally run another function here after it finds that it can't solve it and return it. So yeah, there's things to work on, but hopefully you've seen the fact it works. We've got something that produces a solution. I'm not sure why it wasn't working on them 7x7s, because I'm sure I've had it working on these boards, but yeah, maybe not, I don't know. So yeah, we've got that to do. There's a lot of little bugs in it as well. So for example, if it doesn't find a board, it'll just crash. It would be nice for it to return like some sort of error function, like nicely presented. There's a lot of other functionality you could add to the solve thing, as I've already talked about, adding other functions down here. There's probably more that I forgot. Adding some sort of thing where it could iterate through the levels might be nice. So say it did this level, and then after this level it clicked next level, and then did this one, and we could just see like how far it can get through. That might be quite nice to add, and see what the first level is it gets stuck on. I could even do that, and then say for the first level it gets stuck on, that would be the one I would code to get it to work for that one. Like not specifically for that one, but you know, just implement some rules that would generally solve that one. And then see how far it goes, and then do the same again. That could be the way I like gradually improve it. I'm not sure, we'll see. But if you've got any ideas, let me know. I might post this code in the section below, the comments below. Sorry, the description below. So yeah, let me know what you think. Let me know if this is stuff you're interested in, and hopefully it's not too long. Hopefully someone's at least enjoyed watching this, and that'll be it. So thanks for watching, and I will see you on the next one.